So in continuation with our code converters, today we are going to see binary to gray code converter. So I suggest that you all should copy this truth table first, that is binary to gray code. Can you all see this? Karthik or Anushka, can you confirm this? Can you all see the PPT?
Yes, sir.
I hope there is no noise from my microphone. So here, what we are going to precisely see today is uh, that uh, how to convert the binary to gray codes. And this is really important because in digital communication, we have to do some kind of coding, and that is the reason why we generally go for these particular gray codes. So here, A, B, C, D, they are your inputs. They are the inputs, and the number of inputs is 4. And here you can see that G3, G2, G1, and G0, they are your outputs, and the number of outputs is 4. So we have 4 inputs and 4 outputs. Each of the outputs is dependent on each of the inputs. That is, G3 is dependent on A, B, C, and D. G2 is also dependent on A, B, C, and D. And G1 is also dependent on A, B, C, and D. So we will be using a 4 variable K map, that is precisely 2 raised to 4, that is 16 cell K map, to determine G3, G2, G1, and G0. So based on yesterday's discussion, I would like you to start developing the K map for G3, G2, G1, and G0. So here there is a typical pattern that we will observe while converting the gray codes. Here you should also note that there is no G4, because in gray code there is no such thing as valid gray code or invalid gray code. Whatever may be the binary sequence, we can always determine the gray code of it. So here we are not really interested in G4. So simple 4 inputs and 4 outputs. So if you have copied the truth table, just say done, TT done. Just write TT done. Okay. So I can see some responses, that is TT done. Okay. Yeah. So now let's go ahead one by one. Should I wait?
Yes, sir.
Yes, sir.
Oh, okay, I'll wait for another 2 minutes. So in the meantime, if you have any doubt, you can see that based on this, so the gray code of 1000 is nothing but 1100. So how did I do? This bit and this bit is the same. and then I XOR this. 1 0 is 1, then 0 0 is 0, and then 0 0 was again 0. So we XOR this, then we XOR this two, then we XOR these two. That is 0 0, and then we get these two bits. So like that, you can do it for every sequence to fill the truth table. So you don't have to actually remember this truth table. You can simply create the gray code on your own and simply go ahead. So you can also check a few things here. That is, G3 is the same as A. G3 is the same as A, and G2, G1, G0 are slightly different. G2, G1, G0 are slightly different, and in that also there is a pattern. So if you can keep in mind that pattern also, you can go faster, or you can take simply apply the logic of gray code and get the truth table. Okay, great. So I can see many have completed the truth table. So let's go quickly to the next one. Now you can see that first we are going to calculate G3. So for G3, A is 1. A is the you can see that 8 onwards, 8 to 15. Here, this is 8 and this is 15. They are 1. Others are 0. So calculation of Boolean function for G3. So I want you to fill the key map for G3 and tell me what is the value. Post the value in the chat box. G3 is equal to A. Omkar is the first one to answer that. Very good. Sumant is the next one. Let's see. So this is the K map. Okay. Yeah. So if this is the K map, that's perfect. We are looking at these terms, that is 8, 9, 10, 11, 12, 13. They are, and 14 and 15, they are ones. And simply speaking, you take octave, and that is going to be A. So G3 is going to be equal to A. So that is the first step. The second step is, now you go to G2. Tell me what is G2. Let's see what is G2. Okay, A bar B plus AB bar. Let's check how. Okay, so if you look at G2, then from 4 to 10, from 4 to 10, it is 1. That means 4, 5, 6, 7, 8, 9, 10, and also 11, right? So B bars, C, Omkar's and Suman's answer is different. So let's see who is giving the right answer. I want many of you to post the answer, please. Come on, do the K map. Okay, Atharva also has given the answer. Shubham, A bar B, Hemant, okay. So you can see that the answer is coming out to be A bar B and AB bar. Let's check that. So 4, 5, 6, 7, and 8, 9, 10, and 11. So these are the places where we'll put a 1, and that will give me two chords straight away. You can see that. Uh, so the first chord will give me A bar B, and the second one will give me A B bar. So the answer is G2 is equal to A bar B plus A B bar. Okay, good. So let's go to the next one. So please correct this. This is G3. Sorry, this is G1 only. Okay, G1 according to Atharva it is BC bar and B bar C. Okay, Sumant. Okay, let's see how. So 3, 4, 5, and 6. 2, 3, 4, and 5 are 1. Asmita, this is the answer of the previous one or this one? G1 or G2?
So the previous one.
Okay, then it's right. So these are the positions of ones. So you can see two chords, and now this will be the first one will be B C bar, and the second one will be B bar C. So that is the right answer. Atharva is the given the right answer. So G1 is BC bar plus B bar C. Okay. So should I wait for you to write the K map or should I go ahead? So just notice the places where things are one. Based on that, you should be able to write the K map. Let's go to G0. So for G0, we have 1, 2 as 1. This is G0. This is 1, 2. Then we have 5, 6. Then we have 9, 10. And then we have 13, 14. So these are going to be the positions of the ones. And obviously you can see now C bar B plus CD bar. Okay, great. Deepak has given right answer. Shubham, Gaurav, okay, great. C bar B plus CD bar, that is G0. Now I want you all to open DSCH. Now I want you all to open DSCH. I want you all to open DSCH and implement this function implement all these four functions in DSCH. Implement all these four functions in DSCH. So yesterday I have told, okay, Yash, great. Asmita, C bar D, and Asmita, it's not A B bar.
Sorry, sir.
A B नहीं है ना?
हाँ सर चुकलं ते.
Just check that. Okay. So my circuit will look somewhat like this. So this is G3 itself. This is G3, and here we have, so it was A bar B plus AB bar is nothing but A XOR B. That is why I'm using a XOR gate. Then here we had B bar C plus BC bar. That is why I'm using B XOR C XOR gate again. And here we have C bar D plus CD bar. That is why again I'm using here a XOR gate. So C XOR D. So that is my G3, G2, G1 and G0. Now this is G3 is A. This is A bar B plus AB bar. B bar C plus BC bar. C bar B plus CD bar. So anyhow you can write that inside the OR term, doesn't matter. So that is why purposely I have written this here like this. You can write B bar C first plus BC bar also, no problem. So I want you all to implement this in DSCH. So I am just uh, going to my DSCH to show you the implementation. So I'll just say keep and then go to DSCH file, just open. So we have binary to BC, binary to gray code. So this is how the circuit will look. And if you just simulate this thing and check 1100, so it is 1010 because 1 will come as it is, that is G3. Then 1 plus 1 is 0, that is why G2 is 0. 1 plus 0 is 1, that is why G1 is 1. And 0 plus 0 is 0, that is why G0 is 0. So this is how you should check after every circuit needs to be checked like this. Okay, so you can see this again, one coming as it is, then 1 is 0, then again 1 is 0, and then 10 is 1. So that is why G0 is 1. So implement this function and put the screenshots in your chat box. Or if you are not having this, if you are on mobile phone, then draw this logic diagram. Then draw this logic diagram. So for your practical exam, I can give you any circuit and you have to just implement that. So the strategy is very simple. I may give you the truth table, I may give you minterms, I may give you the logic function directly. From that you have to build the truth table, and from the truth table you will apply K-map, and after applying K-map you will minimize and implement the logic function. Yes, so I want to see who is implementing this first on DSCH. Yes, I am waiting. G3, G2, G1, G0. In the meantime, if somebody has a doubt, you can just unmute and ask me. I will take those doubts, especially in the truth tables. So I can understand that you may have a doubt in the truth table. So if you have that doubt, please ask. Is Anushka there today? So keep that DSCH open only in the background. We may require it every now and then. You can't unmute yourself. Okay, that is pretty weird. Okay, no problem, but you are there. Okay, so I am waiting for the first implementation and then we can go ahead. So you can try out many different combinations. First is 000, then you have 001, then you have 00010. This is 3, this is 4, this is then 5, then this is 6, and this is all three are 7, then we have 8, then we have 9, then we have 10, then 11, then this is 12. Okay. Okay, good. What you all can do is, you can go to file and write here monochrome. You can go to file and do it in monochrome. Monochrome means the background will become white. The background will become white. Okay. So white backgrounds will be required when you are preparing your journals, because if you print so much of black, your black cartridge will become zero within 2-3 prints. So that is why your background needs to be white. But however, white is not that much pleasing background, so black is always better. So when you're doing, you can do it in black, but when you're printing, you have to print it in white background. Okay, great. So let's go back. Now let's go to the other way around. Let's go to the other way around. That is gray to binary. That is gray to binary. So now my input is gray and my output is a binary code. So I will give G3, G2, G1, G0. They are my inputs and my outputs will be ABCD. My outputs will be ABCD. So that is what I am doing. Now you can populate the gray codes serially. That means 0, 1, 2, 3, 4, 5, so on up to 15. And for this sequence, what is going to be the gray code that you can calculate? So 0 will come as it is. Then 0, 0 is going to be 0. 0, 0 is 1. So first comes out to be 0 only. If you take something very random, let's take this code. So this 1 will come as it is here. Then 1 XOR with 1 is going to be 0. 0 XOR with 0 is going to be again 0. And 0 XOR with 0 is going to be 0. So you write first 0 to 15. First you will write simply 0 to 15. And then you will write the binary code for that. So copy this truth table. Once you copy this truth table, write TT done. So what is happening is, again A and B are similar, but here we have 0 0 1 1, then we have 1 1 0 0, then we have 1 1 0 0, and then we have 0 0 1 1. So this is the slight change. Here also we have 0 1 1 0, then 1 0 0 1, 1 0 0 1, and 0 1 1 0. So C and D, that is the last two columns, are different. If you have copied the truth table, write TT done. Okay, Deepak, I'll wait for another 2 minutes. Everybody should be very clear with the truth table. Truth table is the main thing. From truth table, you are making K-map, and from K-map, you are making logic diagram. So truth table is something that you have to be perfect. And what I have done is I have simply made the gray code of each sequence. That's it. So this side is your output and this side is your input. So the gray code of this, you can see from your previous tables also that the gray code of 10 is this. Okay. So let's go ahead and calculate what is the value of A, B, C, and D. So please note now your inputs are G3, G2, G1, and G0, and that is why here we are not writing now A, B, C, D. We are writing now G3, G2, G1, and G0. So please note this change in the K-map. My input is G3, G2, G1, and G0, and now I am calculating A, reverse, the other way around. So in the first case, we have ones here. So this will give me, what is the first answer? A is equal to what? G3 is not A is G3. Yes, there is a difference. Why
Yes,
G3
sir.
is not equal to A? Because your input is G3, G2, G1, and G0, and your output is E. So when you write G3 is A, it means G3 is your output. No, G3 is your input. So A is equal to G3. Okay, great. So this is pretty simple. When it is octave, it is pretty simple. G3. So A is equal to G3. A is equal to G3. So now you will calculate G2. You will calculate G2. So those who are copying this K map can quickly copy the K map, and then we can go ahead. So I'm going ahead with the calculation of Boolean function for B. So for B, 4, 5, 7, 6, 7 and 8, 9, 10, 11 are 1. 4, 5, 6, 7, 8, 9, 10 and 11. So here we have 1. Okay. So G3 bar G2, G3, G2 bar. Omkar is the first one to give that. Uh, okay. So let's see what is the answer for this. This is going to be G3 bar G2, G3 bar G2, and then we have G3 G2 bar. So B is equal to G3 G2, G3 bar G2 and G3 G2 bar. So this is also this B is also G3 XOR G2. B is also G3 XOR G2, right? Correct. Yes, Sumant, Hemant, Asmita, Shubham, perfect. Atharva, yes, correct. But you can also write it as G3 XOR G2 because you want to do implementation with XOR gate. So let's go to the next one. So tell me the answer for C now. So C and D are critical. So tell me that. So here I want to ask you how many quads, how many octaves and how many pairs? Okay, 4 pairs. So basically here we will have 2, 3, 4, 5. Then we have 10, 11. And then we have 14. Sorry, not 10, 11. We have 8 and 9 and 14 and 16. So these are the places. 2 quads. No. Prathamesh, there are no 2 quads. There are 4 2 cells or 4 pairs.
Yes, sir. Yes.
So these are the 4 pairs. 1, 2, 3, 4. So what you will get here now is this is G3 G2 bar G1. This is G3 bar G2 G1 bar. This thing is G3 G2 G1, and this is G3 G2 bar G1 bar. Check all. Copy this thing first. I want you to copy this K-map because here we have to do a slight Boolean simplification also. So the problem with K-map is that it can reduce, it can detect an AND function, it can detect the OR function, and it can reduce it. But it cannot detect a XOR function. It cannot detect the XOR function. That is the disadvantage of K-map. So we have to look for XORs, and if there is a XOR, we can simplify. So common, if we cleanly see, we can go ahead with these four terms directly because they are in terms of uh, sum of products, that is SOP format. But SOP deals with either and or. SOP and POS, both of them, they deal with only and function or function. They don't talk about NAND function, not NOR function. They don't talk about XOR and XNOR function. So we have to deal with these things slightly separately. Okay. Now Yash has given a big answer. G3 bar.
Sir,
Yash,
sorry, it is wrong.
what is this answer?
Sir, it's wrong. Sorry.
Yes. Now I want you all. So I am keeping this K map as it is. I'm keeping this K map as it is in the side. Okay. So this is G1. G1 will be the sum of all these four product terms. So this is what we actually get. C is equal to this. So you can see the K map on the screen, and this is what you actually get. Now I want you to simplify C. I want you to simplify C using Boolean algebra and look for XOR functions and look for XOR functions. So I'll give you a hint. In the first two, you can see you can take G3 bar common. In the second two, you can take G3 G3 common. So what you will get here is G3 bar outside in the bracket, G2 G1 bar, G2 bar G1, and then you will get G3 G2 G1 G2 bar G1 bar. So you should all be able to write this. Then you should see that first term, this term is actually G1 XOR G2, and this bracket is G1 XNOR G2, G1 XNOR G2, or it is G1 XOR G2 the whole bar. So it is either G1 XNOR G2 or G1 XOR G2 the whole bar. So you can consider this upper bracket as X, and you can consider this lower bracket as X bar, and that is what you will get actually. So that's what I actually did. I wrote the first bracket as G1 XOR G2, The second bracket is G1 X NOR. So this is X NOR and this is X OR. So G1 XOR G2, if I write X, then X NOR will be X bar. So we will get G3 bar X plus G3 X bar. G3 bar X plus G3 X bar. So again you can write this term as G3 XOR of X. G3 XOR of X, or you can also write it as X XOR of G3. Whatever you want. So what you will get is G3 XOR of X, but X is G1 XOR G2. But X is G1 XOR G2 or G2 XOR G1, one and the same. So actually speaking, when the pair arrangement is this way, it is the function is G3 XOR G2 XOR G1. The function is G3 XOR G2 XOR G1. So though there were four sum of product terms, they just boil down to one 3-input XOR gate. They just boil down to one 3-input XOR gate. So this entire function we can implement using 3-input XOR gate. So have you understood this? If you have understood this, just type yes in the chat box. And if there is any doubt, you ask. And go ahead with now calculation of Boolean function for D. Calculation of Boolean function for D. So D will have, here C had 4 terms. Now the D part is very typical. The D part is very typical. Come on, do it. So in the meantime, I'm just keeping this C so that people who have not completed can copy this. And I want others to go and solve for D. Karthik, can you just check whether our lecture is being recorded or not? Okay, so let's go ahead. with D. So with D, let's see how your K-map looks. So it is going to look somewhat like this. So that is 1, 2, 4, 7, 8, 11, 13, 14. So your K-map is this way. Now you can see, if you look at this, you will feel that this is an isolated cell, which is true, they are isolated cells. But then K-maps cannot address XOR gates or XOR functions. So we will have to slightly reduce later on using a XOR function. So let's check that. So we have 8 isolated cells. 8 isolated cells. And each isolated cell will give me, so this is G2, G2, G1, all bar, G0, G3 bar, G2 bar, G1, G0 bar, G3 bar, G2, G1 bar, G0. So whichever is 1, you will keep it as uncomplemented, and whichever is 0, you will keep it complemented. So these are the 8 terms. Sir, we can't take pairs of 2 corners. No, you can't take of the 2 corners. You can't. So you cannot take diagonal pairs. You can only take adjacent pairs even at the corners. Have I answered your question, Divya? If they are adjacent, then yes. But if they are diagonal, no. Horizontal, vertical is possible. Immediate up and immediate down, not immediate down and diagonal. So I want you to all copy these terms in the K-map perfectly. Okay, great. So have you finished this? Now let's go to the reduction part. So if you have are you done with the K-map? So if you are done with the K-map, just write K-map done in the chat box. I can understand it's a big K-map. Okay. So now our function will have 8 terms. Our function will have 8 terms. So that 8 terms, I am listing it now on the next slide. Those 8 terms, I am listing it down on the next slide. So these are my 8 terms. So write D is equal to this equation. D is equal to this equation. This is something that I got directly from the K-map. This is something that I got directly from the K-map. Now you can do some kind of pairing. See what I did. In the first two terms, you can see in the first two terms, in this term and this term, G3 bar, G2 bar, G3 bar, G2 bar are common. So I took that outside, G3 bar and G2 bar. Similarly, in the next term, these two are common, G3 bar, G2 and G3 bar, G2. So I took those common here and here. Similarly, in the next two terms, G3, G2 is common. So this G3, G2 is common to both the terms. So we took that thing common here. And then we have G3, G2 bar, G3, G2 bar. So that term is coming here. Now you can see G1 bar G0 plus G1 G0 bar is one XOR gate. Okay, and the other one is the other XNOR gate. G1 bar G0 bar plus G1 G0. They are the XNOR gates. So I can inside those brackets I wrote the corresponding terms, that is G1 XOR G0 and G1 XNOR G0. Similarly with G3 G2 and G3 G2 bar terms. Now G1 XOR G0 I can take it as X, and G1 XNOR G0 I can take it as X bar. So now what I did is I took these two terms. And out of that I took G1 G0 bar common, and then I took these two terms and I took G1 G0 XNOR common. And then what we will get is this. G3 bar G2 bar G3 G2 is G3 XNOR G2, and G3 bar G2 plus G3 G2 bar is G3 XOR G2. So here again we are having two terms. So let's say if this is X, this has to be X bar, and if this is, sorry, this has to be X bar, and if this is Y, and just make it more clear. So this equation is like, if this is X, this is going to be X bar, and if this is Y, this is going to be Y bar. So this is going to be X Y bar plus X bar Y. So that is going to be X XOR Y, but X is G1 XOR G1 XOR G0, and Y is G3 XOR G2. So that is going to be G1 G3 XOR G2 XOR G1 XOR G0. So I hope you have understood this. G3 XOR G2 XOR G1 XOR G0. Correct, Sanmesh. Perfect. So though the terms may look so huge, but actually it is just a 4-input XOR gate. The 4-input XOR gate. And 4-input XOR gate we can implement using 2 or 3 2 inputs XOR gates. two or three two input XOR gates. So if you have copied this calculation of Boolean function for D, then just write done in the chat box. I want you all to write this because this is a very famous exam question. This is a very famous exam question. Binary to gray is simple, but gray to binary involves a calculation. This is one of the very favorite questions of examiners. Okay, I'll still wait 2 or 3 minutes. Those who have finished calculating all the functions, they can go for implementation of the logic diagram. So those who are on mobile phone can draw the logic diagram in their notebooks, and those who are on computer, they can draw it on DSCH. I will prefer you should always draw on DSCH, and if possible, try to shift from mobile to computer or laptop. Okay, great. Done. Okay. So many duns means everybody is very good at copying, but I want you to solve this. Okay. Okay. So any doubts in this? In any step, just unmute and ask. Any doubt in any step? The step should be clear. Then when you are reading later on, you will understand. But if you have not understood any step, stop me and go tell me to go back to the next slide or whatever and get all your doubts cleared. Okay. So let's go to the next step, that is the implementation of the logic function. So you can see A was simply G3. A was simply G3. Here B was G3 XOR G2. So what I have done is this G3 XOR G2, I have given it to the lower XOR gate. So here also I will have G3 XOR G2, and from here what is coming is G1. So at the output I will get G3 XOR G2 XOR G1. Now this thing will come here. From here what is coming is G0. So we can get G3 XOR G2 XOR G1 XOR G0. So instead of implementing this equation with 2 input XOR, 3 input XOR and 4 input XOR, because 2 input XOR is a different IC, 3 input XOR is a different IC, 4 input XOR is a different IC. So in one IC you will get 4 XOR gates. So with just one IC you can implement this gray to binary code converter. Just with one IC you can convert gray to binary instead of going for 3 different ICs of 3 different 3 input gates. We can go for a single IC with 2 input XOR gates. So you are reducing, what you are reducing here, you are not reducing the number of gates, but you are reducing the number of chips, because though you are using only one gate from the one chip, the other 4 are not used, so that is of no use. So we are optimizing the number of gates. So I want you all to implement this in DSCH. I want you all to implement this in DSCH. So let's go to DSCH, and here we will just open grade to binary. So this is our grade to binary code converter. I am running this. You can see that you can check the truth table. For 1100, we will get the output as 1000. So implement this in DSCH and post it in the chat box. And this time, try to make the background white. Try to make the background white. So what I am doing now is I am trying to club the theory with the practical since we are in online mode, and some part of the practical can be immediately done after doing the theory. So this is what we are doing. So let's do it. Okay, Omkar has implemented it first class. Great. So now you all are getting the hang of it. Omkar, since you have implemented it, uh, please ensure that your file name is not example.schematic. Save it to something else, grade to binary.schematic. Otherwise, what happens is every time you open DSCH, your previous circuit will go away. As a default, it gets stored in example.schematic. Okay, great. So Omkar was the first one to implement this. Very good. So this is the logic diagram right in front of you. So if you have completed the logic diagram, just write LD complete. If you have drawn everything what is there on this slide, just write LD complete. Those who are having laptop or computer should implement this on DSCH. I want to see more diagrams. So after this, we will do an exam problem. It is very small, but you have to introspect that properly. Okay, Shubham has implemented it on DSCH. Great. So Omkar and Shubham, since you have made these diagrams, try to convert it into a symbol. Try to convert it into a symbol. Yes, Suman, correct. Even Sanmesh. Try to convert it. Sanmesh, you have to put one output on the last XOR gate. Put one output LED on the last XOR gate. Sanmesh, did you copy that? So try to convert it into a symbol. So whatever circuit we make, we should try to convert it into a symbol so that we want to use it next time, then we can only pick up the symbol. We don't have to again build the circuit from scratch. Okay, yes, great. So try to convert it into a symbol. So how to convert it into a symbol? You can go here, go to file, go to schema to new symbol. So by default, it is giving you G3, G2, G1 and G0, but ABCD positions are slightly different. So let's check that. So A, I want at the top, so I'll make it 1, this 2, this 3, and this 4. So I'll just refresh it. And if you say OK, now you can insert that symbol that you have made. So you can insert that symbol here. So all you can do is just put 4 LEDs. So those LEDs are somewhat overlapping, but that's fine. And just to avoid so many, I'm just using a keypad. So if you just simulate this thing, you can see that I think the grounds or something are getting shorted. So we check. You can just change it to and to just check the connections whether they are right or not. And so just to test the symbol, just forge the symbols also. So try to make it into a symbol. So actually, if you are making a symbol means what? You have actually designed the IC. So in the lab, if you would have been in the lab, I would have given you some IC. So it is coming gray. I don't know why. It should not come. Let me just check it once. Okay. Okay. So you can see now that if I give 3, the gray code of 3 is, if I give gray code of 3, then the binary of that is coming out to be 1101. So you can check that if the gray code of 3 is, if the gray code that you give is 0111, you will get the corresponding gray codes. So that's how you create this anyways. So I'll just save it for our reference. Okay. Now let's go to the next problem, which is an exam problem. So just take it down.
हेलो सर.
Try to read this.
हेलो
Yes.
सर, वो सिंबल वाला पार्ट फिर से बताओ ना.
So here what you need to do is go to file when your circuit is ready. So I'll remove this thing. Save this. Can you see my screen?
Yes sir.
So go to file. Then here you will go to schema to new symbol. So this editor will automatically take all the inputs and the outputs. It can detect that G3, G2, G1 is input and A, B, C, D are outputs. So it is giving you these inputs on one side and outputs on the other side. So you can make this symbol big or small by using these options, and you can name this file here and then say OK, and the schema gets created in the same folder with an extension of .sym. So if you want to get that symbol, you have to select here file type as symbol.sym. So you will see only sym. These are all only symbol files. You can see the extension is .sym only, and then get that thing here. So actually this circuit, whatever you made here, is now this black box. So if you want to use this circuit in some other circuit, then you don't have to start with gates. You can just have this box with input and output. Inside this box, there are 3 XOR gates connected in a certain way. Got it?
Yes sir.
Yeah. Okay. So let's go to the problem. Come on, read the problem. A 4-bit binary number. A 4-bit binary number. So please note, first thing, how many bits? 4-bit binary number is represented by the variables A3, A2, A1 and A0. So you are representing it using A3, A2, A1 and A0. Okay, Shubham has made that good. Great. So where A3, A2, A1 and A0 represent the individual bits with A0, so obviously they are saying that this A0 is LSB and your A3 is going to be the MSB. Okay, that is understood. Design a logic circuit. Design a logic circuit that will produce a high output. Design a logic circuit that will produce a high output whenever the binary number is greater than 0010 and less than 1000. Greater than 0010, that means for 3, 4, 5, 6 and 7, not even 8, 3 is greater than 2 and 7 is less than 8. So from 3 to 7, the outputs will be high. So in a way, they are indirectly telling us that we are having a logic function f, which is a3, a2, a1, a0, whose minterms are 3, 4, 5, 6, and 7. So for this, we have to design a logic circuit. For this, we have to design a logic circuit. So first step would be the truth table. So truth table, for that first you should know how many number of bits, 4. So number of variables are also 4. The number of possible combinations are 2 raised to 4. That is 16. So that is my inputs will vary from 0000 to 1111. So that is what I did. My A3, A2, A1, A0 are changing from 000. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have 11, 12, 13, 14, and 15. And these are my outputs. So you can see here, if my input is greater than this, input is greater than this means here, and less than 8 means this. So all these have to be ones. All these have to be ones. That is my output is high for this combination. That is what it is given. Now we know the output. So there are 4 inputs and there is only one output. So we have to make the K-map only once. So that is why the K-map is only once, but we have to understand what is written in the problem. So copy the truth table. Once the truth table is done, do you want to go back and see this? Right. Write the solution. This is an exam problem. Step 1, truth table, number of bits 4. Number of variables is also 4. Number of possible combinations is 2 raised to 4. So if you have finished this slide, just write done so that I can go to the truth table slide. Okay. So I am going to the next slide, that is the truth table slide. Or should I wait one more minute? Has everybody done? Is everybody done with this? Okay.
1 minute, sir, please.
Yeah. Should we go ahead with the truth table? Those who have understood can start building the truth table with A3, A2, A1, A0 as the inputs and just one Y as the output. And then apply the condition. So you should look for the condition. In this problem, the condition is greater than this number and less than this. That means this is 2 and this is 8. So greater than 2 and less than 8 means that is going to be 3, 4, 5, 6, and 7. Not 2 and not 8. Why? Because 2 will be equal to 2. It will not be greater than 2. And 8 will be equal to 8 and it will not be less than 8. Oh, great. Divya has given the answer directly. Good. Let's check that, Divya. So this is the truth table. Please copy the truth table. Once you copy the truth table, write TT done. And then we shall check, Divya, the answer. Divya, if let me check your answer, A0. I think there is a problem in your answer, Divya. Just try to reconsider your K-maps. So once you have completed truth table, write quickly done so that we can go ahead. Okay, Suman, go ahead with the K-map. There is just one output which is dependent on four inputs. So let us try to check whether your answer matches Divya's answer or not. Parts. Okay, great. A3, A2 bar. A3, A2 bar. Is it A3, A2 bar or A3 bar A2?
Sir, A3 bar A2 and
Okay.
plus A3 bar A1 A0.
3 bar A1. Parts, but your answer is something different only. What you have typed is different.
Yes, sir, that was a mistake. So I just
Okay. A3 bar A1 A0, right? And then you have A3 bar A2.
yes, sir.
That is the right answer. Okay. A3. Okay, Divya also has given the A1 A0. It's not A2. Divya, it's not A2. Don't hurry. You have got the K map correct. So I'm going to the next. I hope everybody has copied the truth table. So I'm going to the K map. So please understand that the min terms are 3, 4, 5, 6, 7. 3, 4, 5, 6, and 7. So my K map will look like this. My K map is going to look in this way. So I will have one quad. I will have one quad and I will have one pair. I will have one quad and I will have one pair. So the answer is now there on your screens. A3 bar, A1 bar, A0, A3 bar, A1 bar, A0 plus A3 bar, A2.
Hello,
Right.
sir.
Yes.
Hello, sir.
Sir, there is a mistake in the K map. It should be in three's place, and you have put it in one's
Third
place.
column. Third column.
Uh,
Sir, 3.
oh, yes, 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 yes. You are right. Okay. So let us rectify that thing. Okay. I think when I put the ones, I shifted. Okay. So let's do it within 1 minute. So we should have a one here. So let me reconsider our answers. So this will come here and now some things can change. Okay, so this will become simply It will become simply A1. I hope I am right. Hope I am right. Is it okay now? Is that okay?
Yes, sir.
Yes, sir. Yes, sir.
So let me just check the next answer also along with it. So that is the change. So implement this function in DACH. Implement the function in DACH. So I think you can implement this with a small change here. So our terms are A1, A0, A3 bar. So here we will have this should come here. That's the only change. So please note that change. So the first term will give me A3 bar, A1, A0, and the second term is A3 bar, A2. So if you have implemented this, well and good, but I hope you can now implement this in DSCH and no need to make a symbol because this is just for a dedicated application. So if you want, you can make, but you may not be able to use it anywhere else because the probability that you will get the same thing somewhere is very low. So no need to make a symbol. You can just try out the schematic or you can just note this logic diagram. Okay. So I'm going to the next problem now. That is BCD to XS3 converter. Now see, we have already done this. BCD was initially binary. We have seen binary to XS3 and binary to whatever. So now we want to see BCD to XS3. BCD means binary coded decimal. So binary coded decimal, as in we want to find out the XS3 of only BCDs. We are interested in XS3 of only BCD numbers. BCD numbers are from 0 to 9. So I am interested in XS3 of only BCD numbers. I am not interested in XS3 of other than 0 to 9. That is why my truth table becomes like this now. You can see that here we have 0 and here we have 9. So we start from 3. So we start from 3. Just give me a minute. So we start from 3. Okay. 3, 4, like that. This is 3. I think there is some error here. So don't worry. I'm just. So first XS3 of 0 will be 3. XS3 of 1 will be 4. So I'll write 0, 1, 0, 0. Then here we have 0, 1, 0, 1. Then we have 0, 1, 1, 0. Then we have 0, 1, 1, 1, that is 7. Then we have XS3 of 5 will be 8. Then we have 9. Then we have 7 XS3 is 10. XS3 of 8 is 11. And XS3 of 9 will be 12. Now we are not interested in XS3 of 10. We are not interested in XS3 of 11. Why we are not interested? Because 10, 11, 12, 13, 14, 15, they are not BCD numbers. They are not, they don't fall in BCD. That is why you can see that here, you can see that here, after 9, I have put all don't cares. After 9, I have put all don't cares. So from here, these all are don't cares. These all are don't cares. So now you will write E3 in terms of ABCD, E2 in terms of ABCD, E1 in terms of ABCD, and E0 also in terms of ABCD. And tell me what is the final answer. Give me the 4 functions, E3, E2, E1, and E0. Once you have copied this truth table, just write TT done. And this is actually 3 and this is 12. XS3. Okay, Sumant is done with the truth table. Sumant, can you go ahead with E3, E2, E1, and E0 K maps? Okay, has everybody completed with the TTs so that we can go to the next? So here A, B, C, D are your inputs. E3, E2, E1, E0 are your outputs. Okay, I am moving ahead. Has everybody completed the truth table or not? I can see only one response. I'll wait for 1 minute then. Okay, so let's go ahead with the calculation of E3. So E3, you can see that uh, 5 onwards, 5 to 9, we have ones. So here you have ones, 5, 6, 7, 8, and 9. You have ones, and rest all 11, 10, 12, 15, and 14. They are don't cares. They are nothing but don't cares. So the truth table, sorry, the K map is going to be this way. The K map will be this way. Now I want to know how many octaves, how many quads, how many pairs. I want to know that. This is also a famous question which is asked in the exam. So how many quads, how many octaves, and how many pairs? Type your answers in the chat box. One 8 cell, one 4 cell, one 2 cell. No, one 8 cell is right. One octaves, two chords with overlap. Perfect. Sumant is the first one to give the answer. Now, Sumant, let's see whether your octaves are correct or not. Can you write the function? A, B, C plus B, D, Omkar. Okay. So this is one octave. This is one chord. This is another chord. Are these the octaves and chords that you have got, Sumant? Divya, E3, E1, E2, E0, E2 are outputs. They are not inputs. So your function is always in terms of input. Okay, Suman. So this is A, this is BD, and this is BC. Right. Sanmesh is also right. A plus BD plus BC. So Sumant again The first one to give the answer. Good, Suman. So this is E3. Let's go to, so please copy this K map. Please copy this K map. Don't care, you can consider it 1 as per your convenience. That is the reason why even with 2 1s we could make a octave. Even with 2 1s we could make a octave, simply because those ones were in a position such that we could build a octave with don't cares. So that is how it is. So please copy this E3 K map, and those who have finished this, go to E2. Okay, so I'm going to E2. So let's look at E2. What are the positions of the ones? So the position of ones are like this: 1, 2, 3. Then we have 4, and then we have 9, and then we have these don't care positions are fixed, because for the last 6 combinations we are putting don't care. So for every K map, 10, 11, 12, 13, 14, 15 are don't cares. Omkar, okay, E2. Let's check Omkar. I'm waiting for somebody else also to give the answer. How many quads and how many pairs? That's my first question always. Your answer seems to be right, but let's verify it. Omkar, 2 quads and 1 pair. Perfect. That is the right answer, Omkar. So this is the K map that you should get. So this is the first pair. This is 1 quad, and this is another quad. So these are the terms that you should get. Shubham, there is no A. You will get A only when there is an octave. You can 3 variables will get eliminated out of 4 only if there is an octave, but there is no octave, no? So did you get that, Shubham? Shubham, did you get it? I think Shubham has logged out. Okay. So this is the answer for E2. Please write it down. B, C bar, D bar. Then we have D bar, D. And then we have D bar, C. Okay. Sanmesh has given the answer. Sanmesh, just match your answer with what I have written. Yes, I think it is correct. Yes, it is correct. Shubham, I think you have corrected your answer. Okay, good. Okay. Yeah, there is a lag. I think even when I change the slide, there is a slight lag. So that is okay. Don't worry. Okay, so let's go to E1. the calculation of E1, we have 0 is 1. So we have 0, then we have 3, then we have 4, then we have 8, and all these are don't care set. So your K map would come out to be like this. The K map would come out to be like this. So two quads, perfect, C bar, D bar, and CD. That is right, Omkar. So you can use a XNOR gate also for this function. You can also use a XNOR gate for implementing this function. So this is my quad, another quad. The first quad will give me C bar, D bar. The second will give me CD, and E1 becomes equal to CD bar, C bar, D bar plus CD. That's right. E1 is right. Yes. Two quads. So somehow I am not now getting the confidence that some of you are still making silly mistakes in K-maps, but try to avoid that. And I think if you understand K-map perfectly, it will be nothing like that. And if you have any silly, stupid doubt about K-map, please post it on the group or make me wait after the lecture. I'll answer that as best as I can. Okay, let's go to E0 quickly. So E0, so let us first mark the don't care. They are the simplest. 10, 11, 12, 13, 14, and 15. They are don't cares. And then we have 0, 2. Then we have 4, 6. And then we have 8. Okay, Sumant and Omkar. So today there is somewhat a competition between Sumant, Omkar, and Shubham. They are, I can see consistently they are giving these three answers. Three are consistently giving the answers. Along with, there are many, but there are these three are the first one to answer, which is very good. So I am noting that. Very good, Omkar, Shubham, and Prathamesh. This speed is very important, especially in exams like GATE and these government exams where you have to solve really very fast, because there are like around 60 questions which you have to solve in an hour's time, and uh, a true engineer should give a solution within a certain amount of time only. There is no, the solution is of no use if it is coming after an infinitely long time. So the speed is very important. Good. So this is my one octave. That's it. We'll cover all the ones, and that is D bar. So E0 is going to be equal to D bar. So now you can think of implementing this thing using this logic diagram. So the logic diagram is there in front of you. Yes, I missed Sanmesh also today. So Sanmesh also is there along with the other. Good. So let's look at the function. Just now we did BCD to XS3. So this is that thing, E3 to E1. So you can always check this thing. Absolutely no problem. 109 will give me 12 and 0 should give me 3. So you can see that the last two are 1, 1. So that's 3. Now For this also you can consider making a symbol. For this also you can consider making a symbol. Karthik, are you able to see my PPT now? I'm just doing a audio check
Yes, sir.
and my voice is not breaking, I hope.
No, sir, not breaking.
Okay, so implement this logic function quickly. Implement the logic function and put it in your boxes. Okay, so should we go ahead? So E3 is BD plus BC plus A. So just post this logic diagram in the chat box. You can just go to the previous logic diagram, say save as, and do some change and post it. So this is, I can understand, this is a big logic diagram. So those who are doing it on DSCH, very good. Otherwise, note it down in your notebook because ultimately you have to write also in the exam. So you should have the hang of both. And the next question will be BCD to gray code. Next will be BCD to gray code. So same thing, last 6 combinations will be don't care, but this time you will calculate gray code of only BCD numbers, that is from 0 to 9. 0 to 9. So when we did binary to gray code, in that same truth table, in the in the truth table of binary to gray, in the truth table of binary to gray, if you replace the last 6 combination with don't cares, if you replace the last 6 combination with don't cares, that is going to be BCD to gray. That is going to be BCD to gray. So that is something that I am giving you for homework, and you have to implement that and tell me, or rather if we can do it here, let's see. So if you have copied down this logic diagram, can we go to the next? we will do one more, that is BCD to gray today. And for homework, you can take it as XS3 to BCD. For homework, you can take it as XS3 to BCD. BCD to XS3 is there in front of you. Now we have to go the other way around. XS3 to BCD. The valid numbers in XS3 are from 3 to 12. The valid numbers in BCD are from 0 to 9. So now your target should be 3 to 12. So I want you to think and make the truth table. Answer anyways, I'll give you through my notes. So it is already there in the PDF that I am circulating with you. Okay. I cannot see any logic diagrams. Okay. So are you posting the logic diagram? Can you unmute and talk somebody? Karthik, are you getting this? Anushka,
Yes, sir. I'm getting it. I'm drawing just it. I'm done drawing logic diagram.
okay. So whenever you all are drawing this logic diagram, just look at the function and draw. Don't look at my logic diagram and draw. It is difficult to trace sometimes. But it is easier to look at the logic function. BD means take a AND gate and put B and D inside it. Next is BC, then take a AND gate and put B and C inside it. So that way it is going to be simple. Don't try to actually copy the logic diagram. Look at the logic function and draw. It will be easier. In this E1 you can draw it using a XNOR gate also. In this diagram, E1 you can draw it using a XNOR gate. That's also fine. So here E1 you can implement this. Instead of this, you can simply draw a XNOR gate and connect these two inside it. So one XNOR is also enough. So this you can do it using XNOR. Okay, so it's 12 o'clock. So what we will do is we will take a break of 15 minutes and exactly at 12:17 we will resume. In the meantime, if somebody doesn't care for a break, then they can start with the next one, that is BCD to gray code. BCD to gray code. BCD is very important for us because binary coded decimals is something that we use all the time everywhere. So we are not interested in much of binary to XS3, but yes, BCD to XS3 is going to be important for us. So let's look at that. The next one would be BCD to gray. So I'm going to the truth table and it's a break officially now. So 12:17 we will resume back. Okay, Shubham, great. Good, very good. Now make a symbol file of this because it's a converter, no? It's a code converter. So you can convert it. And you can also see the Verilog file of this. So it automatically populates all the wires, all the outputs, all the inputs, and all the gates.
Hello, sir.
Yes, Vishwas, tell me.
Hello, sir. How to get that gray code? I am still confused in it. Means how to get BCD to gray code? Can you please explain?
BCD means it's just a number, no? So let's look at this thing. So what do we do in gray code? The first bit we replicate as it is. Then you will take XOR of this. 1 0 is 1. So you will get 1 here. And then you will take XOR of the next two. 0 0 is 0. And then you will take the XOR of the next two. That is 0 0. So you get 0. So like this you do for all. Got it? But
No,
only
sir.
we
Can you
will.
explain again?
Okay. So do you know binary to gray code conversion?
Ah,
Do you
yes,
know
sir.
binary to gray code? So same thing I am doing here. Okay, so let me just explain again. If I have a number 1001, how to convert this to gray? This 1 will come as it is, right?
Ah, yes, sir.
Then I will XOR these two. 1 0 is 1. Then I'll XOR these two. 0 0 is 0. And then I'll XOR these two. 0 1 is 1. So the gray code for 1001 is 1101. That is here.
अच्छा हाँ सर ये एकदम स्टार्टिंग में किया था ना ये सर सब
Ah,
एग्जाम्पल्स किए थे
yes.
ओके ओके
So similarly, you can take 7 if you want. 0 1 1 1. So 0 will come as it is. 0 1 is 1. 1 1 is 0. Again 1 1 is 0. So you can see here, if you look at 7, this is 0 1 0 0. Understood, Vishwas?
हाँ यस सर
So like this, you have to populate the entire table. Now you have to find out BCD to gray. So I am calculating the gray codes of only BCD numbers. That is from 0 to 9. That is 0 0 0 0 to 1001. And from 10 to 15, I write don't care because they are not BCD numbers. So whatever their code is, we don't care.
ओके अच्छा टिल 9 इट वुड बी सिमिलर टू बाइनरी
Yes,
द ग्रे कोड
yes.
ओके अच्छा हाँ ओके
Because
सर
we are dealing only with BCD, na?
हाँ
That's
यस सर
that's why.
ओ ओके ओके थैंक यू सर
Yeah.
just due to not revising this has happened
You need to look at the previous thing because now one thing will be linked to another. So you need to keep on revising the things. And I think I have sent you the notes and PPTs and all relevant material. So just have a look at that.
हाँ ओके सर ओके ओके थैंक यू सर
Okay, so let's start and go ahead with the next one, that is BCD to Gray code converter. So this is the last Gray code converter for the day, and then we can start with adders and subtractors. So we are going to look at some circuits today. So let us quickly do this. So I want you all to calculate G3, G2, G1 and G0 in terms of A, B, C and D. So they will be something similar to the previous one, but let's see. So what I will suggest is that keep your binary to gray code converter in front of you to understand BCD to gray code converter, and then try to see whether they are similar or not. Can somebody give me an audio check?
Yes, sir.
Yes, sir.
Okay. So you are able to see the truth table. Once you have drawn the truth table, just write TT done so that we can go for the analysis of G3, G2, G1 and G0. Okay, Prathamesh has done it. Great. Prathamesh, Sumant and Asmita, go ahead with G3, G2, G1, G0 calculation using K-map. Pratik, go ahead with the calculation of K-map. Okay, so let's look at the calculation of K-map. First starting with G3. So G3 means your K-map is going to be, so like I said, the last six combinations are don't care. 1, 2, 3, 4, 5. They are don't care. And in place of 8 and 9, you will have ones. In place of 8 and 9, you will have ones. So this is the K-map that you will see. Okay, great. G3 is A, pretty fast. Oh, Gaurav has given all four. Great. Let's check whether he is right or not. G3 is G3 is A. Gaurav, G3 is going to be
Yes,
simple.
sir.
Yeah. Okay. So G3, one quad, one octave, and that is why out of A, B, C, D, three variables get eliminated, and what remains is only A. So G3 is equal to A. Okay, great. So everybody has understood. G2 is A plus B, or is it A XOR B you are trying to say, Vishwas? Okay, A plus B, right? So how, what are the, where do will we write don't cares? 10, 11, 12, 13, 14 and 15 are not BCD, so we don't care about it. And then 4, 5, 6 and 7 along with 8 and 9. So here you will get two octaves. Here you should get two octaves, G2, and one octave will be A and the other octave will be B. So Vishwas has given the right answer. Great, good. So G2 is A plus B. Similarly, G2 is going to be A plus B. Divya right, Shubham right, Pratik correct, Omkar is also correct. Prathamesh, G2 is not just B. Prathamesh,
Yes, sir. Yes, sir. I corrected
there are
that.
two
Uh,
octaves.
yes, sir.
Okay, so let's go to G3 or G1. So G1 means again you mark 10, 11, 12, 13, 14, 15 as don't care. And here we have 2, 3, then 4, 5. I think that's it. So these are the positions which are ones, circled are ones, and crossed are don't cares. So let's check. We have two quads, B, C bar and A, B bar, C. Vishwas, when there is a quad, Vishwas, whenever there is a quad, please remember that two variables will get eliminated. Two variables. So at any cost, if there are two quads, then you cannot get a three variable term. So if you have taken a three variable term, it means you have taken a pair. You forgot to take the quad. Is it right, Vishwas?
Yes, sir. Sir, in
Yeah.
the position of 8, 9, 10, 11, 11, I didn't write X. That don't care. That's
Ah,
why.
okay. So that is what. So from the answer only, I can make out that you have taken a pair. Okay. So these are the terms BC bar and B bar C. So BC bar plus B bar C is nothing but what is it? It is nothing but BX or C. And quickly tell me G1, G0, sorry. So let's go to G0. So again 10, 11, 12, 13, 14 and 15 are don't cares. And we will have ones in these positions 1, 2, 5, 6, and I think 9. Yes. So Suman has given the answer. Omkar, let's check. So first is your K-map should look like this, and then you do the grouping in this way. So all ones get covered. No need to care for the don't care because their name is only don't care. You may or you may not care about them. So C bar D and CD bar. Okay, correct. Omkar, your answer is right. Or CX or D, correct. Shubham and Atharva are also equally right. Asmita also, yes, correct. So this is what you will get. G0 is C bar D plus CD bar, and this is the BCD to gray converter. This is going to be your BCD to gray converter. So what is the change in the logic diagram? Can you all identify the change in between binary to gray and BCD to gray? Logic diagram wise, check it. Check the change. So you can see when it was binary, when this thing was binary, for binary, here also we had a XOR gate. But when it became BCD, that one XOR gate, this G2 changed. This G2 changed to OR gate. This G2 changed to the OR gate. So that is the slight change that you can observe. So in the exam, sometimes we will ask you draw binary to gray. So you will draw very happily. And then I will ask you on the same logic diagram a question that what is the change in this circuit for BCD to gray. So you should be able to tell that the G2 XOR is now simply replaced by a OR gate. So implement this, copy down this diagram or implement it in DSCH. So first one is G3 is A, G2 is A plus B, G1 is B bar, C bar plus B bar C. So initially, what I mean to say is G2 was A XOR B for binary to gray, and G2 has changed to this is OR gate, this is XOR, and this is XOR. So for binary, this thing has become or was rather XOR. So if you have drawn this logic diagram, just write done. So let's see the DSCH for it. File open. BCG to gray. So that's the change. And you can see that instead of a XOR gate, now we are using a OR gate. So you can just use some random function. 1 0 1. You will get 1 1 0 1. And this is something very random. Okay. So the next thing that you are going to do is access 3 to BCD code, but as a homework, access 3 to BCD code, but as a homework. Now let us go to something called as arithmetic circuits. And like I told you, addition is like the basic operation. Even when we did code converters or different types of codes, we saw that the basic operation is addition. So let's go to that. So the next thing that we are going to do is arithmetics, and what we are going to broadly look inside this is adders, subtractors, mux, demux, adder, subtractor, mux, demux, and maybe some decoders. So these are the basic entities as far as a microprocessor is concerned. So a microprocessor has got a ALU. It is called as arithmetic and logic unit. Today it is not called as ALU, rather it is called as GPU, that is graphic processing unit. So graphic processing unit means it is having a processor which can do all basic operations very fast, which involves basically additions and subtraction. Okay, great. Shubham has completed it. Perfect. Good. So that is what we are going to look broadly in this part. So first thing is adder. So in a digital computer, a variety of data are processed in digital form. Processed means the word processed itself means there are lots of additions and subtractions. And we all have seen that we used to do subtraction by one's complement or two's complement or ninth's complement or tenth's complement. So what we actually used to do is add only after taking a complement. So subtraction involved complements plus addition, and addition was simply adding 2 using XOR logic. So let's look at that. Among other functions, addition is the most basic operation. That means every operation can boil down to addition. So that is why the most basic or the most discussed entity in digital design is the adder. The most discussed entity in digital design is a adder. Now, while addition, you may have a carry from the previous addition, or you may not have a carry from the previous addition. So there can be two cases. Either you may have a carry from the previous addition, or you may not have a carry from the previous addition. The adder which does not account, the adder which does not account for the carry from the previous stage is called as half adder, and the adder which accounts for the carry from the previous addition is called as a full adder. So now we will see half adder and full adder in detail. So first is just a recap of addition. If there are two bits A and B, 0, 0, sum is 0, carry is 0. So this we have already done. For the first input, if it is 0, 0, the addition is 0. The sum is 0. Carry is also 0. If we have a second condition, that is input is A and B is 0, 1, then the A and B are the two inputs. Sum is 1, carry is 0. Then next one, A and B are 1 and 0. These are my A and B. So sum is 1, carry is 0. And finally, we have A and B both ones. So sum is going to be 0. Sum is going to be 0. And carry is going to be 1. Sum is going to be 0 and carry is going to be 1. So what does this mean? What does this mean? A and B are my inputs, and these two are my outputs. These two are my outputs. So when we did this, we actually did not see the circuit which can actually do this. We did not see actually the circuit which can do this. So now we are interested in, okay, I know how to add, that is fine. But if a circuit has to do this, how to design that particular circuit? So that is our primary concern here. So write first. Now you can start writing from here. First, half adder. Start writing half adder. So truth table is something like this. You can see half adder, I told you, does not account for carry from previous stage. Does not account for carry from the previous stage. What is the meaning of that? When I am adding A and where I am adding B, I am not asking whether there was a carry from the previous stage or not. So I am simply adding, assuming carry from the previous stage is 0. Carry from the previous stage is 0, or I'll write Cin is 0. So that is, so what you can see here is basically just a truth table of the addition that we have already seen on the previous slides, and also the addition that we have been using till now, that is sum is 0 and carry is 1, something like that. So now I want to write what is the equation for s is equal to what. I want to write s as a function of a and b, and I also want to write carry as a function of a and b. So how to do that? So I can do that using K-map. Here, how many inputs are there? Here the number of inputs are 2. So the K-map that I can use is, so number of cells in the K-map is 2 raised to 2. That is going to be 4. So I will use a 4 cell K-map, which is basically a 2 cross 2 K-map. So that is what I do. I take this K-map first, that is 2 cross 2. For 0, 0, the output is 0. Then I fill this K-map. So you can see that in these two positions, we are having ones. In these two positions, we are having ones. And now these both ones are isolated cells. And each isolated cell will give me one term, that is A bar B. And the second one will give me AB bar. Similarly, so I can say sum is equal to what? A bar B plus AB bar. And here we all know that S we can simply write now as A XOR B. A XOR B. That means if I want to take a sum, or if I want to calculate a sum term, if I want to calculate a sum term, I require a XOR gate. If I want to calculate a sum term, I require a XOR gate. Similarly, if I want to now do carry, so you can see that carry is 1 only when A and B are 1. So for this combination 1 1, my carry is 1. In all other places it is 0. So that is the reason why now we again get one isolated cell, and the value of that will be simply AB. And this is basically, I can write carry is equal to A dot B. So to implement, so C will be A dot. So to implement a sum, I require a XOR gate, and to implement a carry, I require a AND gate. To implement a sum, I require a XOR gate, and to implement a carry, I require a AND gate. So please copy these K-maps and these terms in your notebooks, and once you are done, just type done in the chat box. Okay, I'll wait for 1 more minute, please. All should write this down in their notebooks. Practice only will make you perfect. Okay. So now the logic diagram of this circuit. Now the logic diagram of the above circuit. So like I said that we require one XOR gate and one AND gate. So the logic diagram would be like this. So first is sum is A B bar plus A bar B and carry is AB. So here basically you will get A bar B plus AB bar, which is A XOR B, and this term is also A XOR B, and this is A dot B. So that's how it is. So draw this. So if you have drawn this logic diagram, just tell me done, LD done, right? LD means logic diagram. LD done. And we can also test this in DSCH. So I'll just open this half adder. It's always better to see the simulation. So this is your half adder. You can see and verify the truth table. 1 1, sum is 0, carry is 1. 0 1, sum 1, carry 0. 1 0, sum 1, carry 0. And when both are 0, sum is 0 and carry is 0. So that is good. Okay. Logic diagram. So I have just simulated the logic diagram for you, and you can also do it in DSCH if there is some time, or you can do it later. So I'm going to wait for another minute for all of you to complete. So just draw this diagram, please. Okay. Okay. So the symbol of the half adder. Now, if you have drawn the logic diagram, just write below that only. The symbol of the half adder is like this. The symbol of the half adder is like this. You can just show two arrows and write your AB, and based on A and B, you get two outputs. One is sum and the other one is carry. One is sum and the other one is carry. One is sum and the other one is carry. So you implemented this particular circuit. Now if you want to implement it Yeah, I'm back. Okay. So I had lost my connection for a minute or so. So am I audible, Shubham?
Yes, sir.
Okay. So this symbol you can create in DACH by after making the function. So just copy this symbol also. So sometimes in the exam they will ask you write a short note on half adder and full adder. So what is expected is truth table, then calculation of sum, calculation of carry using K maps, logic diagram, and then the symbol of the half adder. So this is for 5 marks, and the following are for full adder also we have to do the same thing. So let us see that, and together it will make one 10-mark question. So moving to full adder. So like I said, sum and carry. Now you write the truth table of full adder. Now how to understand this truth table? You should understand it like this. See here. A B can be 0 0, A B can be 0 1, A B can be 1 0, and A B can be 1 1. Now for each AB, for each combination of AB, the carry from the previous addition, the carry from the previous addition can be 0 or 1. For 0 1 combination of AB also it can be 0 1. The carry from the previous combination can be 0 1, and the carry from the previous combination can be 0 1. So whenever you are adding two bits, the two bits can be 0 or 1 only. So A and B are your inputs. But if you have to account for carry from the previous stage, then that previous stage carry can also be 0 or 1. So that gives rise to 8 combinations of A, B, and instead of C, now I am not writing C, but I am writing C in. C in, that is the carry from the previous stage. And now my output will be, obviously one output will be sum only, and the other output will be C out. So A and B are the bits that I am trying to add. A and B are the bits that I am trying to add. C in is the carry from the previous addition, which can be either 0 or it can be 1. So when I add all these three A, B, C, I'll get either sum and I'll get carry. So carry from the previous stage, I am calling it as C in, and carry from the current addition, I am calling it as C out. Okay, so draw this truth table, and once this truth table is done, write TT done. Okay, I'll wait for another half a minute till you write the truth table. Okay, so now I have clearly written here my inputs are A, B, and C in, and my outputs are sum and carry. So now what I am expecting is sum as a function of A, B, and C in. And what I'm expecting here, C out as a function of A, B, and C. So sum will be a function of A, B, and C, and carry C out will also be a function of A, B, and C. So while writing K map, now there are how many inputs? 3 inputs. Inputs is equal to 3. So 2 raised to 3 is equal to number of cells. That is, now I will require a 8 cell K map, which will address 3 variables A, B, and C. So if I am writing a K map like this, here I'll write A, here I'll write B and C. Here I'll write B and C. So let's go to the calculation of sum and carry. So first is calculation of sum. First is calculation of sum. So write exactly the way you are seeing on the slide. First step you write calculation of sum S. Calculation of sum S. So this is the K map. From the truth table you can very easily identify that. From the truth table you can identify that this is going to be the K map for sum, because this is my position. This is actually what? 0, 1, 2, 3. This is 4, 5, 6, and 7. So you can see in positions 1, 2, and 4 and 7, you are having ones. So that is where I have written ones. So all the cells are isolated. There is no quad possible, there is no octave possible, and there is also no pair possible. Please see here, I have not written C. I have written C in because now my input is not C, it is C in. So that is why A, B, and C in. So now we will take isolated cells, and 4 isolated cells will give me 4 terms. 4 isolated cells will give me 4 terms. So we will have A, B bar, C in bar, that is the first term. Then this will give me A bar, B bar, C in. This will give me A, B, C in, and this will give me A bar, B, C in bar. A bar, B, C in bar. So isolated cells in this fashion, please recall, we have seen such a fashion even while doing gray codes, and that culminated into a XOR logic. So we will try to find out whether we are able to get some XOR logic here also or not. So here, this is the sum equation that we are getting. Now what I am doing is I am grouping certain terms. So for example, I'll group the first and the last one, and I'll group these two. So that grouping is given in the next step. That grouping is given in the next step. Now I will take C in bar common from the first 2 terms. I will take C in bar common from the first 2 terms, and I will take C in common from the next 2 terms. So I will get this particular equation. Now you can very well see that the first one is AB bar plus A bar B. So that is my XOR, and this is going to be XNOR. The first bracket is XOR and the second bracket is XNOR. So you can consider this in this particular fashion: A XOR B and A XNOR B. So if I consider this as X, then NOR XNOR will be simply X bar. So that is the next step. So I took A plus A XOR B as X and A XNOR B as X bar, and then I got C in bar X plus C in X bar. But what is X? X was X was simply A XOR B. So what we are going to get here is X XOR Cin, where X is equal to A XOR B. So instead of X, I will substitute A XOR B and XOR Cin. So here again the sum was A XOR B XOR Cin. So we can now generalize that if I want to add 10 bits, then it will be A XOR B XOR C up to A XOR J, something like that. So sum is nothing but XOR operation. Sum is nothing but XOR operation. So please copy this quickly and then we will go to the carry part. It's already 1 o'clock. We'll just extend not more by 5 minutes, not more than 5 minutes. So if you have done copying this, then we can go to the calculation of sum. So if you have done copying sum, write sum done. Okay, Sanmesh and Asmita, can you think on similar guidelines and start calculation of carry? You already have the truth table for carry. Tanish, you can also go on with the calculation of carry. Okay, great. So many of you have calculated it fast. I am just simplifying so that everybody understands. So some steps might be, you may skip some steps, but I am not skipping any. So let's go next, calculation of carry. So let's go to the calculation of carry. So in the calculation of carry, Divya has already given the answer, BC in AC in AB, that's right. But how? So this should be your K map for the carry. Then you have three pairs. You have three pairs. You don't have any quad, you don't have any octave. So three pairs means if there are three variables, one variable gets eliminated. So for the first pair, we have AC in, that is right. For the second pair, we have BC in. For the third pair, we have AB. So Divya, your answer is right. There is absolutely no problem in that. But generally, implementation wise, we do something more. Implementation wise, we are doing something more. So we get a carry equation which is like this. We are getting a carry equation which is like this. So in the books, you will never see AB, BC in and AC in. You will see something different. So I am only arriving at that particular term. You may all write the carry as what Divya has written, or you may write the carry what now I am going to solve. What I am going to solve is something that you will find in your books. Any reference book or any textbook will have what I will solve now. But at that time, you should not have any confusion how we came at that particular term. So that is why here is the solution for that. So now I appended once. I appended once here. There is no harm in ending with 1. Any term can be ended with 1 and it still remains the same term. But 1, I can write it as A plus A bar in the first case, and in the second case, I can write it as B plus B bar. That is the complement and the uncomplement. The OR of that is always going to be equal to 1. So the next step is about that. So one I am writing it as A plus A bar and the other one I am writing it as B plus B bar. In the second term A was not there, that is why I wrote A plus A bar. in the third term, B was not there. That is why I wrote B plus B bar. Then I will open the brackets. I will open the brackets, multiply each term inside. And then you can see, that A, B, C in and A, B, C in appears twice. A, B, C in and A, B, C in appears twice. So if you have something like this, x plus x is equal to x only. That means if this is repeating twice, then we can just have that once and skip one of these terms by using OR law. So I now skipped one of this and simply wrote the other four. Now in the first two terms, I will group first two and then I'll group these two. You can see A and B are common in the first two terms, and you can see C in is common in the next two terms. So if I take AB common outside, I will get 1 plus C in, and if I take C in common, I will get A bar B plus AB bar. So
Hello,
that
sir.
is what, yes, yes,
Sir, first term does not have C. And why will not add C? पहले term,
first term doesn't have C, means I didn't get it.
sir,
Are you talking?
first term have AB only, na? Then we should, na?
Yeah, so I have taken AB common. Na? I have not taken
No,
C in common.
sir, our equation is AB plus BC plus AC. Then second term doesn't, and third term doesn't have B. Then first term doesn't have C. Then you not add C.
So that is okay because I am arriving at a, so you are asking me why I have not added C here.
Yes, C plus C, na?
Yeah. So it is not necessary to add it. So that's what I'm saying, that it is not a compulsion. You need to check whether I am maintaining the equality or not. So I am maintaining the equality. In the given question I had AB. So here also I have AB. So I can always do that. It's up to me. So I think you will get your answer when I show you the next step. So here 1
Okay.
plus anything, 1 plus any variable, 1 plus x is always 1. Whatever may be the value of this x, it can be 0 or 1. 1 plus 1 is always 1. 1 or 0 is always 1. So this term will become 1, and this term is nothing but a XOR b. This term is nothing but a XOR b. So this becomes, so the carry becomes a c is equal to ab plus c in into a XOR b. So what I am trying to do here is, what I am trying to do in this simplification is, I am trying to relate, I am trying to say that sum of A and B is also a part of C in or C out. Sum of A and B is also a part of C out. So C out has got carry from the previous stage as well as the sum of the current stage, as well as the sum of the current stage. So that's what I'm trying to say here. Are you understanding this? Why I did not take C?
Yes, sir.
Yeah. So I am trying to arrive at this. That is why I am not taking it that way. Okay. So this is something. So you will always find this equation in the books. That is C out is equal to AB plus C in from the previous stage and A XOR B. Now you can see sum was A XOR B XOR C, and carry equation is there on your screens. And carry equation is there on your screens. So the implementation of this would be this way. So I have three inputs A, B, and C in. So here I get A XOR B. Here I get C directly. So here I'll get A XOR B XOR C. Now here you can see that here I am getting what? C in, and here I am getting A XOR B. So just now who asked me the question? Can you just tell me your name, please?
Gaurav Goswami.
Gaurav, are you understanding why I am doing this now? Because I want to take this XOR output only when I want to calculate my carry.
Yes, sir.
And here the other term is A and B. So here I will get AB, and here I will get C in into A XOR B, and my output C out will be AB plus C in into A XOR B. So this is the logic diagram for the full adder, and the block diagram would be something like this. So you can draw the logic diagram as well as the block diagram, and that's it from my side for today. So this is basically a full adder. So if you just look at the DACH and we try to open full adder, so the circuit will be like this, and if we try to simulate it, you can see that when the carry is 0 from the previous stage, it acts like a half adder only. When the carry is 0 from the previous stage, it acts like a half adder. 0 0 sum is 0, 0 1 1 0 sum is 1, 0 1 sum is 1, carry is 0, and 1 1 carry is 1. But when there is a 1 here, then it is different. When the C in is 1, 0 0 sum is 1, 1 0, because 1 plus 1 is sum is 0 and carry is 1. Then when all three are 1, we saw when we were summing that when there are 3 ones in a row, my sum is 1 and my carry is also 1. So that is exactly what a full adder does. It accounts for carry from the previous stage. So if I want to do a 4-bit addition, I will require 4 full adders. If I want to do 10-bit addition, I will require 10 full adders. If I want to do 64-bit addition, 64-bit addition where we require generally in microprocessors where if you are moving one file to another location, so you are only incrementing the address, and address lines are 64-bit. So if you want to increment the address location, you will require an adder. So you will require a 64-bit adder. So 64-bit adders means you will have 64 full adders, and 64 full adders will have 5 gates inside it, and each gate has got 4 transistors. So 4 into 5 is 20, 20 into 64. Those many number of transistors you require to implement a 64-bit adder to do an increment operation of 64 bits. So the logic is that way. Anyways, I will be highlighting this when I do 2 types of adders. One is called as ripple carry adder and the other one is called as carry look adder. So probably that will be there in our next session. So kindly copy this diagram here. And if there are any doubts, you can ask me. Do not log out. I am taking your attendance. So is everybody in or some people have left? I think I will ask. Please ask them to join.
Hello.
Yeah.
Hello, sir.
Yes, sir.
So Okay.
Hello, sir. I am Anusha Sara.
Yeah. Tell me. Yes. Tell me.
So, is this mini project meeting?
No.
So, I didn't call actually. I received a call.
Yeah. So you are supposed to attend this lecture, right?
Yes, sir. Hello.
Sir was recording attendance meeting. Sorry, attendance, taking attendance. So he called all of you.
I think they were not there in the entire lecture, I guess.
Acha, is it so? Okay.
Sir, you are on mute.
If there are any doubts, you can ask me, or now you can officially log out. I have taken the attendance. See to it that you attend the lectures, and after the first I will be putting up a defaulters list. The defaulters list will be put up, and you will have to justify your absenteeisms on the days you were not present. So if you were present for most of the sessions, then forget about it. You don't even have to care about it. But those who have not been attending a single class, uh, I have to report that to the department. Department shall get in touch with you on that. So that's it. If there are any questions, I'm here for another 10 minutes and you can go for your lunch.